Welcome to your personalized deep dive.
Oh, cool.
Today we're tackling the world of language agents.
Okay.
Those AI systems, using large language models or LLMs,
Yeah.
to interact with the world.
Right.
You sent us a paper titled Cognitive Architectures for Language Agents,
Mm-hmm.
which dives into a question that's captivated AI researchers for decades.
Okay.
How do we build truly capable language agents?
Yeah.
And could they be a stepping stone to language-based general intelligence?
It's a fascinating area of research.
For sure.
And this paper explores the history of the field,
Okay.
connecting early concepts like production systems to these cutting-edge language agents.
I was intrigued to see the authors draw parallels with those older systems.
Yeah.
It feels like we're about to uncover a hidden lineage in AI,
Exactly.
like we're looking back to the roots.
Yeah, it turns out that the ideas behind early AI, like string manipulation using rules, are surprisingly relevant to understanding modern LLMs.
Interesting.
You can think of it like this.
Okay.
Imagine those old Mad Libs games.
Where you fill in the blanks to create a sentence.
Right.
Early production systems operated on a similar principle,
Interesting.
using rules to manipulate strings of symbols.
So even though these systems were much simpler,
Right.
they laid the groundwork for understanding how to manipulate information using rules.
Precisely. And as these systems evolved, they became capable of surprisingly complex behavior.
Oh, wow.
A classic example is the SOAR architecture,
Oh, okay.
a cognitive architecture designed to model intelligent agents.
Now, when I hear cognitive architecture, I think of something that mimics how our brains work. Is that on the right track?
Absolutely. SOAR has distinct memory systems,
Okay.
just like our brains do.
Interesting.
It has long-term memory for storing knowledge and procedures, and working memory for handling the current situation and goals,
Okay.
using rules called productions.
Okay.
SOAR decides what actions to take based on the information in its working memory.
So it's...
This creates a decision-making loop, driving the agent's behavior. So SOAR, even though it's an older system, gives us a framework for thinking about how an agent can perceive,
Yeah.
process information, and then take action.
Right.
Is that a fair summary?
You've got it. And here's where things get really interesting.
Okay.
The authors of the paper argue that LLMs,
Mm-hmm.
despite their vast complexity and probabilistic nature,
Yeah.
can actually be viewed as a kind of modern production system.
That's a fascinating connection.
Yeah.
I wouldn't have immediately linked these massive language models with those rule-based systems.
It might seem counterintuitive,
Yeah.
but instead of those fixed rules we see in classic production systems,
All right.
LLMs have learned an immense set of potential string manipulations
Wow.
from the massive data sets they're trained on.
So instead of having explicit rules, they've developed an implicit understanding of language patterns and relationships.
Exactly.
Okay.
This makes them incredibly flexible and capable of generating human-quality text,
That's impressive.
but it also makes them less transparent. Unlike those rule-based systems,
Right.
we don't know precisely what rules an LLM is applying,
Right.
only that it's learned them from the data.
That lack of transparency must raise some interesting challenges when we're talking about building agents
It certainly does.
that can operate in the real world.
And it highlights a key difference between traditional AI systems
Yeah.
and these new language agents.
Okay.
Instead of being programmed with specific instructions,
Right.
we're now trying to guide these LLMs toward intelligent behavior.
Interesting.
Think about it like this.
Okay.
Instead of giving an agent a set of rules,
Mm-hmm.
we're now giving it a prompt, a starting point, and letting it figure out the rest.
That's where the concept of prompt engineering comes in, right?
Precisely.
It's like we're trying to steer the LLM in a particular direction
Yeah.
without explicitly programming its every move.
By carefully crafting the input text or prompt, we can influence the kind of output we get from the LLM.
So you're saying it's a way of shaping its behavior?
Yeah.
Without having to define every possible rule or scenario.
Precisely.
So prompt engineering is becoming a crucial tool for controlling these incredibly powerful language models.
It is.
It's almost like we're having a conversation with the AI,
Right.
guiding it towards a desired outcome.
That's a great analogy.
Cool.
And it highlights a fundamental shift in how we think about building intelligent systems.
Okay.
We're moving away from explicit programming and towards a more collaborative approach,
Interesting.
where we guide the LLM's learning and decision-making processes.
It sounds like we're moving towards a world where AI systems are less like tools and more like partners, capable of understanding our intent and collaborating with us to achieve complex goals.
That's exactly where this research is heading.
Okay, cool.
And the paper you shared dives into a framework
All right.
designed specifically for building these sophisticated language agents.
So a framework for these agents.
Yeah, it's called CoALA,
CoALA.
short for Cognitive Architectures for Language Agents.
Okay. CoALA, the framework for building these next-generation agents.
Yes,
It sounds like we're about to delve into the heart of this deep dive.
we are.
Exciting.
And CoALA offers a fascinating blueprint for how we can organize these complex systems,
Okay.
combining the power of LLMs with the insights we've gained from cognitive science and traditional AI.
Before we get into the details of CoALA, can you give us a high-level overview of what makes a language agent different from just an LLM?
Sure.
What are the essential ingredients?
That's a great question. It's not enough to just have an LLM that can generate text.
Right.
A true language agent needs to be able to interact with the world,
Okay.
to take actions and learn from the feedback it receives.
Yeah, so it's not just about generating text.
Right.
It's about using that text to do something in the world,
Yeah.
whether it's controlling a robot,
Yeah.
navigating a website,
Right. Yeah.
or even just having a meaningful conversation.
You've hit the nail on the head.
Cool.
Language agents need to be grounded in the real world. Whether it's physical, digital, or social,
Makes sense.
they need to be able to perceive their environment,
Yeah.
take actions, and adapt their behavior based on the outcomes of those actions.
That makes sense. It's like they need a way to bridge the gap between the world of language and symbols
Exactly.
and the world of action.
And that's where CoALA comes in.
All right.
It provides a framework for thinking about how to design these agents,
Okay.
how to give them the capabilities they need to act intelligently in the world.
Okay. I'm ready to dive into CoALA.
Let's do it.
What are the key elements of this framework?
Well, let's start with the foundation memory.
Memory.
CoALA recognizes that language agents need different types of memory to function effectively. It outlines several key memory systems,
Okay.
each with a specific role to play in the agent's operation.
So just like our brains have different types of memory?
Yes.
CoALA is saying that these language agents also need a variety of memory systems
Right.
to handle different kinds of information. What are some of these memory types?
CoALA outlines working memory,
Working memory.
which acts as a sort of mental scratch pad,
Okay.
holding information that's actively being used in the current moment, like goals and recent observations or even intermediate reasoning steps.
Okay, so like short-term memory.
Right.
Okay.
Then there are the three types of long-term memory.
Let's dive into those long-term memory systems. What are they?
Okay.
And how do they contribute to the agent's overall intelligence? Okay, let's unpack these different types of long-term memory. You mentioned three, right?
That's right. CoALA suggests episodic, semantic, and procedural memory as the key components of long-term memory in a language agent.
Those sound familiar. Aren't those terms used in cognitive psychology to describe human memory as well?
Yes, exactly. And that's one of the cool things about CoALA. It draws inspiration from how our own minds work. So
Yeah.
episodic memory is all about specific experiences. It's like a diary of the agent's past, storing memories of particular events and interactions.
So instead of just knowing facts, the agent actually remembers specific events that must make its experience of the world much richer, right?
Absolutely. It allows the agent to learn from its past in a more nuanced way. Imagine an agent playing a game. Instead of just remembering the rules, it can remember specific moves. It made the outcomes of those moves and even the emotions it felt during the game.
That's amazing. So if episodic memory is like a personal diary, what about semantic memory?
Semantic memory is more like an encyclopedia. It stores the agent's knowledge about the world, facts, concepts, relationships, everything it knows about its environment.
So it's the difference between remembering that time you went to Paris and knowing that Paris is the capital of France. One is a personal experience, the other is general knowledge.
That's a perfect analogy, and both are essential for an agent to function effectively in the world. Finally, we have procedural memory, which is all about knowing how to do things. It stores the agent's skills and procedures.
Ah, so this is where the agent stores its repertoire of actions, its knowledge of how to perform tasks and achieve goals.
Exactly, and here's where CoALA gets really interesting. It proposes that procedural memory can exist in two forms for language agents. First, there's the implicit procedural knowledge embedded in the LLM itself. The LLM, through its training, has absorbed an enormous amount of knowledge about how language is used to perform actions and achieve goals.
So the LLM, just by being trained on massive amounts of text, has already learned a lot about how to do things in the world simply by observing how humans use language.
Precisely, but CoALA also includes the concept of explicit procedural memory, which is stored as code. This code can be written by human programmers or potentially even learned by the agent itself.
Now, that's a mind-blowing idea, an agent that can learn new skills by actually writing its own code.
It's cutting-edge research, and it raises some fascinating questions about the future of AI. But for now, let's get back to the CoLA framework. So we've talked about memory, but what about the agent's ability to interact with the world? That's where the concept of actions comes in.
Okay, actions. I'm guessing this is about how the agent actually does things in the world, right? It's not just sitting there thinking, it's taking action to achieve its goals.
Exactly. CoLA divides actions into two main categories: internal actions and external actions. Internal actions are all about interacting with the agent's memory systems, retrieving information, reasoning about it, learning new things. External actions are the ones that actually affect the world outside the agent.
So internal actions are about thinking and learning, while external actions are about actually doing things in the world.
That's a great way to put it. And these external actions are what we call grounding actions. They're the bridge between the agent's internal world of language and symbols and the external world, whether it's physical, digital, or social.
So grounding is all about connecting the agent's internal representations with the real world, allowing it to have a real impact. Can you give us some examples of these grounding actions? What kinds of things can these agents do?
There are many exciting examples in the research. For instance, there's Saycan, a language agent that can control a robot in a kitchen environment. It can follow instructions like, bring me a snack, by understanding the language, translating that into a sequence of actions, and then controlling the robot to execute those actions.
That's incredible. It's like having a personal robot chef who understands your every command. Are there other examples of these grounding actions in different domains?
Absolutely. There are agents that can play text-based games, navigate websites, even interact with other agents in simulated social environments. All of these examples showcase the power of grounding actions to connect language with real-world outcomes.
It sounds like we're moving towards a world where language itself becomes a powerful tool for controlling and interacting with our environment.
That's exactly the direction this research is pointing towards. But now that we understand how agents connect with the world, let's go back to those internal actions.
Okay, those actions that are all about the agent's internal processes. What are the different types and how do they contribute to the agent's overall intelligence?
Well, as I mentioned earlier, there are three main types of internal actions: retrieval actions, reasoning actions, and learning actions. Each one plays a crucial role in the agent's ability to process information and make decisions.
Let's break those down, starting with retrieval actions. What's their purpose?
Retrieval actions are all about accessing the information stored in the agent's long-term memory. Think of it like a search engine for the agent's mind.
So when the agent needs to remember a fact, a past experience, or even a procedure, it uses retrieval actions to access that information from its long-term memory.
Exactly. Retrieval is a fundamental process for any intelligent system. It allows the agent to draw on its past experiences and knowledge to make sense of the present and plan for the future.
That makes perfect sense. It's like how we humans search our memories for relevant information when we're trying to solve a problem or make a decision. What about reasoning actions? How do those work?
Reasoning actions are where the power of LLMs really shines. These actions allow the agent to generate new knowledge or insights by processing the information available in its working memory.
So it's not just about remembering things. It's about using that information to think, to analyze, to draw conclusions, and even to come up with new ideas.
Precisely, reasoning is what allows the agent to go beyond simply reacting to its environment. It can plan, strategize, and make decisions based on a deeper understanding of the situation.
It sounds like reasoning actions are at the core of what makes these agents truly intelligent. They're not just following pre-programmed instructions, they're thinking for themselves. What about those learning actions? How does an agent learn and grow over time?
Learning actions are all about updating the agent's long-term memory based on its experiences. This could involve adding new facts to its semantic memory, storing a memorable event in its episodic memory, or even modifying its code to learn a new skill.
So the agent is constantly learning and evolving just like we humans do. It's not a static system. It's dynamically adapting to its environment and experiences.
Exactly, and just like with procedural memory, there are different levels of learning. The agent can learn by simply storing new information, or it can go further and actually modify its own code to acquire new skills or behaviors.
Wow, an agent that can modify its own code that opens up a whole new realm of possibilities, doesn't it?
Absolutely.
But it also sounds potentially risky.
hmm
What are the implications of giving an AI that level of autonomy?
It's a fascinating and complex issue. The ability for agents to modify their own code is still largely theoretical,
Okay.
but it's a topic of active research with both exciting potential and important ethical considerations. But for now, let's bring our focus back to the overall decision-making process of a language agent.
Okay. Decision making. We've talked about memory actions, grounding. How does it all come together to allow the agent to act intelligently in the world?
CoLA proposes a decision-making framework based on repeated cycles in each cycle. The agent receives some input, whether it's a new observation from the environment or a goal it needs to achieve.
So it's a continuous loop of perception processing and action. The agent is constantly interacting with its environment and making decisions based on the information it receives.
Exactly. And here's where things get really interesting. Using those internal actions we discussed, retrieval and reasoning, the agent enters a planning stage.
So before taking any action, the agent stops to think things through. It retrieves relevant information from its memory, analyzes the situation, and comes up with a plan.
Precisely. It's like the agent is holding an internal dialogue, weighing different options and considering their potential outcomes. This planning stage is crucial for intelligent decision making.
It sounds incredibly complex. How does the agent actually decide which actions to take? Is there some sort of algorithm that guides its choices?
There are different approaches to this, and CoALA outlines several possibilities. The agent can use simple heuristics or rules of thumb, it can rely on learned values or preferences, or it can even use the LLM itself to simulate the potential outcomes of different actions.
So it's like the agent is running mental simulations, trying to predict the consequences of its choices before actually taking action. That's an incredible level of sophistication.
It really is, and this decision-making cycle continues constantly refining the agent's understanding of the world and guiding its behavior towards achieving its goals.
We've covered a lot of ground here, but I'm curious to see how this CoALA framework translates into real-world examples. Are there actual language agents out there that use this approach?
Absolutely. The CoALA paper analyzes several existing language agents using this framework, and they offer some compelling examples of its effectiveness.
Okay, I'm excited to hear about these real-world examples. It's one thing to talk about the theory, but I want to see CoALA in action. So give us some concrete examples of those language agents using the CoALA framework. What are they actually capable of?
One example that highlights the power of internal actions working in tandem with external actions is REACT, which stands for Reason and Act. It's designed for navigating digital spaces like using a web browser or searching for information. React's design is simple in the sense that it doesn't have separate long-term memory for storing specific facts or past events.
So no remembering fun facts or reliving virtual vacations for this agent. It's all business focused on navigating the digital world.
Exactly. But each cycle, React uses internal reasoning to analyze the current situation, figure out its goal, and create a plan all in text. Then based on that reasoning, it selects an action to carry out in the digital environment.
So it's not just blindly trying different actions. It's thinking things through first, like planning a route before taking a trip.
That's a great analogy, and this combination of internal thought and external action is surprisingly effective, much more so than having an LLM just blindly execute commands.
That makes sense. It's like the difference between randomly clicking links on a website and actually having a search strategy in mind. But what about agents that can actually learn new skills, like you mentioned earlier? React seems a bit limited in that regard.
That's where Voyager comes in, an agent designed to navigate the world of Minecraft. Now, this agent does have long-term memory specifically for storing code. Think of it as a library of skills that the agent can access and use.
So instead of remembering what happened in its last Minecraft game, Voyager remembers how to do things like building structures or crafting tools.
Exactly, and these skills can be combined and reused to achieve more complex goals. For example, to successfully defend itself against a zombie, the agent might need to retrieve and execute the skill of crafting a stone sword.
That's fascinating. It's learning to solve complex problems by breaking them down into smaller, more manageable steps, just like a human would.
And here's the mind-blowing part. Voyager can even learn new skills by modifying its own code based on its experiences. It's like it's writing its own instruction manual as it plays the game.
It's almost like it's evolving, adapting to the challenges of its environment by developing new capabilities. That's both incredible and a little bit unnerving.
I know, right? It's one of the most exciting and potentially challenging aspects of this research, but Voyager is just one example of how language agents can learn and adapt. Another fascinating example, demonstrating how memory and learning can create incredibly rich behavior, is generative agents.
Okay, generative agents. Sounds intriguing. What makes them unique?
Imagine a simulated town populated by AI characters, each with their own personalities, memories, and goals. That's what generative agents aim to create.
Like a virtual world where AI characters are living their own lives, interacting with each other, and shaping their own destinies.
Exactly. These agents don't just react to their environment, they live in it, they form relationships, they make plans, and they even reflect on their experiences.
That's incredible. From a CoLA perspective, how do they use those different memory systems we talked about?
Well, they store their experiences in episodic memory, just like a personal diary. Then they use reasoning to reflect on those experiences, extracting general knowledge and forming opinions, which get stored in their semantic memory.
It's like they're turning those individual events into lasting knowledge and beliefs, shaping how they see the world and make decisions.
Precisely. And all of this is driven by language. Their memories are stored as text. Their reflections are text. Even their actions are determined by the LLM's language processing capabilities.
It's amazing to see how language can be used to create such complex and nuanced behavior. But you mentioned one more example, tree of thoughts. What's special about that one?
Tree of Thoughts is a bit different. It focuses on solving complex reasoning problems, those brain teaser puzzles that require you to think several steps ahead.
So it's like the brain of an agent without the body. No interacting with the world, just pure thought.
Exactly. It doesn't have long-term memory or grounding actions. Its sole purpose is to tackle those tricky reasoning problems.
How does it approach those problems? Is it just using the LLM to brute force a solution?
It's more sophisticated than that. It uses a technique called tree search, where it generates a tree of possible solutions, evaluating each branch and choosing the most promising path. And it uses the LLM for both generating those potential solutions and evaluating their likelihood of success.
So it's like the LLM is playing a game of mental chess with itself, exploring different possibilities and strategizing to find the best solution.
That's a great way to visualize it, and it turns out to be incredibly effective. Tree of Thoughts outperforms other methods on those complex reasoning tasks, showing the power of combining structured search with LLM reasoning.
Wow, we've covered so much in this deep dive, from the basics of string manipulation to these mind-blowing examples of language agents. It's been an incredible journey.
It really has, and the CoALA framework ties it all together. It provides a powerful lens for understanding how these agents work, how they learn, and how they make decisions.
I feel like my understanding of AI has been completely transformed. To wrap things up.
Yep.
What's the key takeaway you want our listener to ponder?
I think the most important takeaway is this. We're at a turning point in AI research. We're moving beyond simply training models to perform specific tasks. We're now building agents that can reason, learn, and interact with the world in ways that were once thought impossible.
And CoALA is a roadmap for building these amazing systems, combining insights from cognitive science with the power of LLMs. It's a glimpse into the future of AI, where language is the key to unlocking true intelligence.
Exactly. And if you think about it, CoALA separates the agent's brain, the LLM, from its body, the grounding actions. This raises a fascinating question. Could we one day have agents switching between different bodies using the same knowledge and skills in vastly different environments?
That's a mind-boggling thought. It's like the agent's intelligence becomes portable, adaptable to any situation.
What an incredible idea to leave our listener with. Thanks for taking us on this deep dive. It's been an eye-opening experience. And to our listener, keep those curious questions coming, because we're always ready for another deep dive into the world of AI. Until next time.